Hello students. So in the previous class we started with Laplace transform, and this is basically the last topic of our course that we want to see the application of Laplace transform to solve ordinary differential equation. So Laplace transform is defined sort of in a way of an improper integral, and we also learnt about the criteria or the condition under which this integral is convergent, or when you have the Laplace transform existing, right? And if the Laplace transform exists, then we can be able to calculate the Laplace transform of several functions. For some basic functions we saw in the examples, but you can calculate other functions as well. The reason why we are learning Laplace transform is that the whatever methods we learned for second order or let's say higher order ordinary differential equations, they can all be tackled using Laplace transform. So it's a very handy tool, and it's really one of the important topics in applied mathematics where you see the applications of Laplace transform. Not just for ordinary differential equation, but you can also solve partial differential equations using Laplace transform. But since that is out of the scope of this particular course, because this is an ordinary differential equation course, we will only look into the application of Laplace transform in ODEs, right? So let us continue our discussion. So we did evaluated some of the Laplace transform for some functions. Just to mention, it has several properties. So the first property is the linearity. That means I think I may have mentioned. So linearity means if suppose Laplace transform of a function ft is denoted by integral from 0 to infinity e to the power minus of st ft dt, then basically ft dt, then basically Laplace transform of c1 f1t plus c2 f2t will be simply c1 into Laplace transform of f1t, Laplace transform of f1t plus c2 into Laplace transform of f2t. So this is very obvious because as we can see, if you write the Laplace transform of this function as e to the power minus f st c1 into f1t plus c2 into f2t, then basically the integral is linear in nature. So it will go to both the terms in addition, and then it will become c1 into Laplace transform f1t plus c2 into Laplace transform of f2t. So this is this. Then the first property or important property is the first shifting property, right? So this is one of the important properties of Laplace transform. So it tells us that if the Laplace transform of ft, Laplace transform of ft is denoted by f of s, then Laplace transform of e to the power at ft will be denoted by f of s minus a, right. So that means if you have a product function in a way that you have e to the power at into, let's say, sin t. So basically we know the Laplace transform of sin t, so it will be Laplace transform of e to the power at sin t as f of s minus a. So whatever Laplace transform of sin t you had, you will just write instead of s, you will replace it by s minus a. So this is a very convenient tool to or convenient result to calculate the Laplace transform when we have a shifting. That means we have shifted from s to s minus a. Third property is change of scale, scale property. So change of scale property says that if Laplace transform of ft is denoted by f of s, then Laplace transform of f of at, that means we have changed the scale from t to at, so it will become 1 by a f of s by a. That means if Laplace transform of ft was f of s, then Laplace transform of f of at will become 1 by a f of s by a. I am not doing the proofs of any one of these results because it is very obvious. You can just do simple integral and you will be able to prove this. So there is really no trick going on here. So these are very obvious to prove. the fourth important property, and it is one of the vital ones because we need this property when we are solving the ordinary differential equation. So, this one is Laplace transform of the derivative, Laplace transform of the derivative. So, we will see how does this look like. So, statement goes like this: let f t be a continuous function and f dash t is piecewise continuous. Remember, for Laplace transform we do not need the continuity, we just need the boundedness of the function. That means even if it is piecewise continuous, it will suffice, right. So, f dash t is piecewise continuous and piecewise continuous in 0 less than t less than or equal to capital T for all t positive, let f t be of exponential order as t tends to infinity, then the Laplace transform of the derivative which is f dash t exists. So, its Laplace transform exists and is given by Laplace transform of f dash t equals to s into Laplace transform of f of t minus f of 0. Kind of looks like a definite integral type formula on the right hand side, right, but it is not exactly that definite integral just from the memorizing point of view. But ideally Laplace transform of the derivative is s into L of f t. So, this is a function of s, this is s and this is a function of s minus f of 0. That means you have to know the value of the function at f equals to 0. That is why having f t to be continuous in the entire 0 to capital T is very vital here. And since we are talking about Laplace transform of f dash t, obviously it does not have to be continuous f dash t. If f dash t is just piecewise continuous, that would also suffice because that is the property or the criteria we need for the Laplace transform. And on the right hand side we have L of f t. So, since f t is continuous, obviously it is I mean stronger than being piecewise continuous. So, you have always bounded and therefore, it will be of exponential order and all that, and its Laplace transform will definitely exist. So, this exists and this has to exist so that you can write down the Laplace transform of the derivative. So, this result helps in a way that if you have a first order ODE, you charge the Laplace transform. So, the f dash x or f dash t term will become L into f t. So, that will become f of s. So, you solve for f of s, it will become an algebraic equation. So, you solve for f of s and from there you again charge the inverse Laplace transform to get your capital F or to get your y back in a way, right. So, if you have a first order ODE, this relation helps us. I mean this theorem or this result helps us a lot. Now, imagine if you have second order ODE or third order ODE or even nth order ODE, then the similar result can be adapted and we can generalize this to a higher order derivative. So, that means you can have Laplace transform of second order derivative f double dash t or f triple dash t, f4, 5 and up to nth order, right. So, in general we have this result. So, if we have a Laplace transform of f and t, Laplace transform of f and t. So, this will become s to the power n Laplace transform of f t minus s to the power n minus 1 f at 0 minus s to the power n minus 2 f dash at 0 minus dot dot and so on minus s f dash f to the power n minus 2 0 minus of f to the power n minus 1 0. So, this is just f. That means as you can see, it is sort of like a polynomial in S, not exactly polynomial because we do not know what will be our L of f t, but kind of like that. I mean, because you have s to the power n, s to the power n minus 1 and so on. So, if you substitute n equals to 1, then in that case it will become s L of f t minus of f of 0, exactly like the previous one. So, this is the general rule which can be derived from the first one, though that means the previous Laplace transform of f dash t. So, from there this actually comes, because if you have Laplace transform of, let us say f double dash t, I will just show you f double dash t. So, f double dash t, then this will become Laplace s into Laplace transform of f dash t minus of f dash 0, right. Now, this one is s into Laplace transform of f t minus, this is t, f t minus f of 0 bracket f of 0, right, bracket close, minus of f dash 0. So, this will become one more s will be here. So, this will become s square Laplace transform of f of t minus s f of 0 minus f dash 0, right. So, this is the required term for second order derivative. You can put n equals to 2 and we can verify this, that it will become s f of 0 minus f dash 0. So, like this, if you continue the induction, you will be able to obtain the derivative for the Laplace transform of the nth order derivative, right. So, this is very straightforward. I am not doing the proof of the previous one because it can be proven very easily by doing the integration by parts. So, you take integral from 0 to infinity e to the power minus f s t into f dash t, then you use integration by parts and from there you will be able to obtain the required result. So, it is also very straightforward. So, we can skip it. And if we have inverse Laplace transform, that means if L inverse of Fs is equals to Ft, if L inverse of Fs equals to Ft, then L inverse of Fs is equals to Ft, then L inverse of Fns equals to L inverse of dn by dsn of f of s, which is equals to minus 1 to the power n t to the power n f of t, where n is from 1, 2, 3 dot dot and so on, right. So, inverse Laplace transform of f n s will be L inverse of dn by dsn of f of s, which is equals to minus 1 to the power n t to the power n. This is property number E, I guess. Then there is a property number f. Suppose Laplace transform of f of t is equals to f of s, right. So, then the Laplace transform of integral from 0 to t f of tau d tau is equals to f of s by s, which is 1 by s Laplace transform of f of t. So, just like we have the Laplace transform for the derivative, we can also have Laplace transform for the integral, and it is just fs by s, right. So, that is the third or sixth property in a way. And another couple of more properties before we can actually jump into solving the examples. So, then we have convolution. Theorem, right. So, let f and g, let the two function f t and g t be of class A. The function f star g, which is, so convolution is denoted by star. So, f star g means there is a convolution between f and g. So, where which is the function f dash g, which is defined as which is defined as f star g equals to integral from 0 to t f of x g of t minus x d of x is called the convolution of the functions f and g, right. So, we are saying that ft and gt be a class A function. So, basically it means that it is of exponential order, piecewise continuous and all those things. Then the convolution between f and g is denoted by star. So, that means f star g, and obviously it is a function of t. It equals to integral from 0 to t fx and then into g of t minus x. This is how we define the convolution. So, it is called the convolution of the function f and g, right. So, then it can be seen that it can be seen that that the following properties hold true, right. So, what is the first property? The first property is f star g is equals to g star f. That means commutative behavior. Okay. Then second one is f star g star h is equals to f star g star h. This is associative property. Third one is f star g plus h, then this is f of f plus h, f plus g, f dot g plus f star h, right. So, f star g plus f star h, this is called as distributive property. Right. So, we have commutative, associative and distributive property. Why we are learning about convolution? So, convolution is a very big chapter. If you especially study in partial differential equations and all, so there you will find out that convolution is quite a big chapter and you have to cover many topics. Here we are just giving the definition and three basic properties, right, that it is commutative, associative and distributive. So, if that happens, then there is a little theorem. It says that let Fs and Gs be the Laplace transforms of Ft and Gt. So, if they are the Laplace transform Ft and Gt respectively, of course, then the Laplace transform of the convolution f star g is the product of Fs and Gs, product of Fs and Gs. In other words, Laplace transform inverse Fp Gp is equals to Fs sorry, this S looks like G. Fs and Gs equals to Ft convolution with Gt, right. So, that means there is a way we can connect the Laplace transform. So, is to be very precise, inverse Laplace transform with the convolution, right. So, inverse Laplace transform of Fs into Gs. So, this is Fs into Gs. There is a dot, that means the multiplication of the two functions. So, Fs into Gs is equals to Ft star Gt, that means the convolution of Ft and Gt. This one is also very easy to prove. So, therefore, the proofs we are leaving. Next property, so I lost the count. So, maybe H, I do not know, E, F, G was the previous one G. So, F and then convolution was G. So, I guess this one is H. So, here again let us say that Laplace transform of Ft is equals to f of s, then Laplace transform of t Ft might lead to minus of f dash s. That means Laplace transform of Tft. So, if you take Laplace transform of Tft, which is equals to minus of f dash s. So, it basically tells us or connects us with the function capital F into t equals to minus of f dash s. That means the minus of derivative of the Laplace transform of f. Right, and this proof is also very straightforward, and from here there is a small generalization that Laplace transform t to the power n Ft equals to minus 1 to the power n dn by dsn of f of s, minus 1 to the power n dn by dsn of f of s, where n is running from 1, 2, 3 dot dot and so on, right. So, that is the Laplace transform for t to the power n f of t, and that is pretty much it, right. So, these are some of the important. So, there is one more property, second shifting property. We will see whether we need in the context of our problems or not, but these are the gist of the results and formulas that is there in the Laplace transform. We can try to solve some examples. So, example 1, find the Laplace transform of sin square at. Obviously, this also should be intuitive when you had sin square x in your integral calculus. So, what you did, you rationalized with 2 and then you wrote 2 sin square x as 1 minus cos 2x, and there you can do the integration very easily. So, here also we will do somewhat similar. So, we have Laplace transform of 1 by 2 and then here 2 sin square at. So, this is Laplace transform of 1 by 2 1 minus cos 2t, and therefore, this will become Laplace transform of half minus cos 2t by so there is another half cos 2t by 2, right. So, this is by 2. Okay, now Laplace transform will go individually. So, 1 by 2 constant and then 1 by 2 out, Laplace transform of cos of 2t. Right. So, from here Laplace transform half. So, that means basically a constant, and therefore, this will become 1 by 2s minus 1 by 2 Laplace transform of cos of 2t. So, this will become s by s square plus 4, right. So, from here I believe we can get half out, and then we have 1 by s minus of s by s square plus 4. So, s into s square plus 4 will become common. So, in the numerator we will have s square plus 4, and that will be minus of s square. So, hopefully it should be 1 by s square plus 4. Right. So, this is our required Laplace transform of sine of a square, sine square at, right. Similarly, we can have t into cos t, t into sine t. We can have something like this also. We have, let us say, this function example, find the Laplace transform of have obtained where f is equals to, we have to obtain the required solution, because t minus 1 whole square, where t is greater or equal to 1, and t is equals to 0 when 0 less than t less than 1, right. So, Laplace transform of f of t is equals to that is what we have to determine, where f t is equals to t minus 1 whole square into when t is greater or equal to 1 and equals to 0 when t is less than 1. So, this is again very simple. Laplace transform of f of t will be integral from 0 to infinity e to the power minus f s t f of t dt. So, now when t is between 0 and 1, it is always 0, and from 1 to infinity we have t minus 1 whole square e to the power minus of s t dt. That means from 1 to infinity this is defined, not from 0 to infinity, because between 0 to infinity it becomes undefined. Now, from here we can do integration by parts, and if we do integration by parts, ultimately we will obtain e to the power 2 e to the power minus of s divided by s cube, right. So, although the function was not continuous, but we do not need the continuity part, we just need the piecewise continuity part, right. So, it is definitely piecewise continuous when t is greater or equal to 1. So, from there we can evaluate this integral, just do the integration by parts, and that will give you your required answer. Just like this, you can have rational function, you can have say something like p r by p minus 2 or 3p minus 2 by p square minus 4p plus 20, whatever all these things are given, you break it down into partial fraction, right, the way you did for integral calculus. When you break it down to partial fractions, then each one of these fractions will be individually handled by charging the Laplacian on this addition. So, it will go term by term, right, and that is how we calculate the Laplace transform. There is not much of calculation involved when we are doing the Laplace transform. So, that is why either I consider one example or many examples, it is the same thing. So, this is what I wanted to tell you about Laplace transform and its application. In the next class, we will start with ordinary differential equation, and we will just apply Laplace transform to the ordinary differential equation, and we will see how the solution looks like, right. So, I will stop here today, and we will continue this discussion in the next class.